Welcome to Math TV with Professor V. This is Intro to Statistics, video lectures for sections 5.1 and 5.2. In 5.1, we're going to start talking about discrete random variables and probability distributions. So what's a random variable? A random variable is a quantitative variable whose value depends on chance. So remember, quantitative variable means that it has a numerical value, and the value of this variable depends on chance, some chance process. So some examples, say the sum of the dice when a pair of fair dice are rolled, right? So the sum could be any number, that's why it's quantitative, from 1 through 12 if you only have 2 dice. But the value depends on a chance process, right? We don't always know when we roll 2 dice what the outcome's going to be. Another example would be the number of puppies in a litter, or the number of students in a statistics class with blue eyes. You could think of probably quite a few more, okay? We're going to focus now on discrete random variables. And a discrete random variable is a random variable where the possible values can be listed. So in particular, it's a random variable with only a finite number of possible values. If you think about it, like the sum of the dice, when you roll a pair of fair dice, it could only take on the values from 1 through 12. We could list them all. There aren't infinitely many options, and it's not going to take on any decimal values either. It's countable. Same thing, number of puppies in a litter, number of students in a class, etc. Now, we're going to introduce a new notation when we're dealing with random variables, okay? And typically, we've used lowercase letters in the past, like X, Y, Z, when we have variables, generally speaking. When we have a random variable, we usually use a capital or uppercase letter. So in your old algebra classes, maybe they're like, oh, find out how many siblings someone has. You would use lowercase x to represent the number of siblings. But if we're describing x now as a random variable, okay, the outcome of a chance process, we're going to switch to capital X, all right? So that's why things are going to be capitalized when it's a random variable. And here's how we would use the appropriate notation. So if you want to describe the event that a selected student has 2 siblings, you would use braces, so these squiggly things, and 2 siblings means capital X is equal to 2, all right? And then if you want to describe the probability of that event, then you just slap a P on the outside, switch to parentheses now, still capital X equals 2. So notice the event by itself has braces, but when we describe probability, then we switch to parentheses, all the while keeping the variable X capital. You could do Y, Z, whatever letter, all right? So just keep in mind, braces here just denotes the event by itself, and then capital P with parentheses, that denotes the probability. All right, that's enough with notation. We'll practice using it. Don't stress too much. It'll come to you naturally as you work through the homework problems, I promise. Now, we do have 2 requirements for any discrete probability distribution. So the sum of the probability of all of the events, X, must be 1. And for all X's, all events, their probabilities need to be between 0 and 1. So no negative probabilities, no probabilities greater than 1, and all of the probabilities of every event should sum up to 1. If these 2 requirements are met, then you got a probability distribution. If either of them is violated, you don't have a probability distribution. Okay, good. So let's look at some examples. First one, from the document American Housing Survey for the United States, published by the U.S. Census Bureau, we obtained the following frequency distribution for the number of persons per occupied housing unit, where we have used 7 in place of 7 or more. Okay. Frequencies are in millions of housing units. So identify the possible values of the random variable y. And here, what we're measuring is the number of persons per occupied housing unit. Persons. That's what we're measuring. So these are the values that y can take on. So for part A, we just have to identify them. Well, here in this frequency distribution, I see the values 1 through 7. 1, 2, 3, 4, 5, 6, 7. Now, B says use random variable notation to represent the event that a housing unit has exactly 3 persons living in it. Okay, so this is just an event, so we'll use braces. And the variable that we're using is y. So y is equal to exactly 3. That's it. Okay, we're just describing the event using the appropriate notation. We're not actually computing anything just yet. Now part C says determine the probability that y is equal to 3. And then interpret in terms of percentages. All right, so to get the probability that y equals 3, I'm going to take the frequency. So the frequency at 3 was 17.0, and then I need to divide by the total. Well, they didn't give me the total, so we got to total it up right now. Okay, so take a second, add up 27.9, 34.4, 17, 15.5, 6.8, 2.3, 1.4. We got to total that all up. And we have 105.3. Okay, so to get the probability that y is equal to 3, I'll take 17.0, divide by 105.3, and that gives me 0.161. I'll just round to 3 decimal places. Okay, and then interpret this in terms of percentages. So what that means, remember we multiply our probabilities when they're in decimal form by 100 to get a percent. So this tells me 16.1% of these occupied housing units are occupied by 3 persons. I said persons instead of people because that's what they put in the table, okay? And then last, they want the probability distribution of y. Okay, so to get the probability distribution, I'm going to take each of the frequencies and divide by the total, 105.3. I already did it for y equals 3, but I got to do it for the rest of the values. So here are the values that y can take on, lowercase, right? 1 through 7. 1, 2, 3, 4, 5, 6, 7. And then I'll make my own little distribution. When you're doing your homework online, you just have to fill in the table. You won't have to be drawing one like this, okay? And then we want the probability that our random variable y is equal to 1 through 7. So for this first one, you would take the frequency that we have up here, 27.9, divide by the total, 105.3, and let's just round everything to 3 decimal places. This is 0.265. And then I'm not going to write out the work for the rest. You can just figure it out. 34.4 divided by 105.3. This will give you 0.327. And then we already had from the previous part the probability that y equals 3. So that's 0.161. For 4, we take 15.5 divided by 105.3. That's 0.147. 6.8 divided by 105.3 should be 0.065. And then 2.3 divided by 105.3 is 0.022. Last one, you should have 0.013. All right, good. Notice all of these probabilities are between 0 and 1, and the sum should be 1 or very close to 1. Sometimes you have rounding error, and if you add up all of these probabilities, you don't get 1 on the dot if you've rounded a wee bit, but it should be awfully close. Okay. Last, we're going to construct a probability histogram. Again, when you're doing your homework in StatCrunch, you're not going to have to make it by hand, but I'll just do it because why not? So this is the probabilities on the y-axis. And then I'm going to have all of the values that y takes on down here. Number of persons. Let's make this straight, please. There we go. Number of persons. And it looks like the largest probability that we have is 0.327. So I can just go up to 0.4. Let's say that's 0.1, 0.2, 0.3, 0.4. Okay, so if there's only one person, the probability was 0.265. So a little more than a quarter of the way up. 0.1. No, more. Oh my goodness. 0.265. I've lost my mind for a split second. Here we go. All the way up here. Okay. That's 1. Shall we switch colors for 2? Yes, let's do it. 2 is going to be over here. 0.327. A lot of homes with 3 people or with 2 people. How many people live in your home? Yeah, for me, it's actually just 2. Just me and my husband. Okay, 3 is 0.161. 0.161. So do 1 and a wee bit more than a half. Like here. Obviously, this is not exact. When you do it on StatCrunch, either they'll have graphs for you to pick from, or you can just generate one using their little tool there. 0.147, a little less than halfway between 0.1 and 0.2. 5 is 0.065, so a little more than halfway up 0.1. Oops, purple. 6 is 0.022, very flat, 1/5 of the way up. 0.022 and 7.013. Oh my. Shall we add a little more? Yes. 0.013. Little baby. Oh, purple, please. Okay, so you get the idea. Very good. Ready to move on? Excellent. The Atlantic Hurricane Database extends back to 1851. Wow. Recording, among other things, the number of major hurricanes striking the U.S. Atlantic and Gulf Coast per year. A major hurricane is a hurricane measuring at least a Category 3 on the Saffir-Simpson hurricane wind scale, meaning with winds of at least 110 miles per hour. As published by the National Oceanic and Atmospheric Administration and the Atlantic Oceanographic and Meteorological Laboratory, the following table provides a probability distribution for the number of major hurricanes Y for a randomly selected year between 1851 and 2012. All right, so use random variable notation to represent each of the following events the year had at least one major hurricane. So at least one means one or more. So that would be the event that capital Y is greater than or equal to 1. All right, at least one means one or more, so greater than or equal to. Exactly 3 major hurricanes we would represent with capital Y equals 3. All right, next one, between 2 and 4 major hurricanes inclusive. So then you would have Y between 2 and 4, and I'm using inclusive, meaning less than or equal to or greater than or equal to symbols. These are inclusive. If it says strictly, then there's no underlined part. That's a strict inequality. Okay, good. They always have to open up towards the larger quantity, so to the right in this case, okay? So make sure these are facing the correct direction. Now, use the special addition rule and the probability to determine, part D, the probability that y is greater than or equal to 1. So let's think about it. The probability that y is greater than or equal to 1 would be the sum of all of these probabilities, 1 through 8, okay? Or can you think of a shortcut? Well, we talked about the fact that the sum of all of the probabilities in a probability distribution, all of these added together is going to equal 1. So a faster way to compute that would just be 1 minus the probability that y is equal to 0, the one that's not included. So that would be 1 minus 0.185, which is 0.815. And if you want to double check, you could sit there and add up all the probabilities for 1 through 8, but this is much faster, right? Since we know the sum of all the probabilities is going to be 1, just do 1 minus the one that you don't need. Okay, what about the probability that y is equal to 3? Well, for that one, you can just go ahead and read straight off the table the probability that they give you for y equals 3. So that's going to be 0.093. And then the last part wants the probability between 2 and 4 inclusive. So that would be the sum of the probabilities for y equals 2 plus 3 plus 4, because we're including 2 and 4. So this would equal 0.266 plus 0.093 plus 0.049. Okay, and then you can add those all up in your calculator. You should get 0.408. All right, good. So that concludes 5.1. Now we're going to look at section 5.2, the mean and standard deviation of a discrete random variable. So the mean of a discrete random variable, the ones that we've just been studying in 5.1, that represents the theoretical or long run average. And remember, we've used mu to represent the population mean in the past. So that's the same symbol or notation we're going to use for the mean of a discrete random variable. To compute it, here's the formula. You add up, that's that sigma, that means add them up, each of the x's, the values that the random variable takes on, times the probability. Okay, we'll work through examples so you can see exactly how this formula works. It's not as scary as it looks. Some other terms that you might hear instead of mean are expected value or expectation. So if you're asked to find the expected value or expectation of some variable, same formula. They're just asking for the mean and they're just using a different name for it. All right. And we also use the symbol mu with a little x as the subscript to denote that the mean is of the discrete random variable x. So you're just being extra specific that, hey, this mu is for the variable x. Okay, you don't always have to put it there, but if you do, just if you see it, don't have a meltdown. Rounding rule, usually in the exercises we'll tell you how many decimal places to round to, but typically the rule of thumb is you want to round the mean to one more decimal place than is present in the variable or outcome x, okay? Or if you have a fraction, just reduce it to lowest terms. Okay, so there's the mean. Now, if you need the variance and standard deviation, here are the formulas. Remember, you really only need to learn the variance formula. Standard deviation, you just take the square root of the variance. So to get the variance, this time you're going to sum up all of the values of the variable squared times their probabilities. And then after you finish adding that up, you subtract the mean squared. So you, even if they don't tell you to find the mean, if they ask for the variance, you do have to find the mean first. Otherwise, you can't compute it. And then this is just telling you, hey, to get standard deviation, you take the square root of the variance, which we know. Okay, that will never change, okay? And again, rounding rule, so you would just use the same rounding rule for variance and standard deviation as for the mean. So just one more than we have in our variable, okay? Let's look at an example so you guys aren't so terrified. I know the formulas can look a little intimidating, but they're really not that bad. First example. A study conducted by a TV station showed the number of televisions per household and the corresponding probabilities for each. Okay, so 1 television, probability 0.32, 2, probability 0.51, 3, probability 0.12, and 4, probability 0.05. Find the mean, variance, and the standard deviation. So first let's start off with the mean. Formula for the mean is the sum of x times the probability of each x. So these are the x values, okay? I'm going to multiply each of them by their corresponding probabilities. So 1 is going to get multiplied by 0.32 plus, why am I adding? Because this sigma, that's what it means. It means add them up. Plus 2 times 0.51 plus 3 times 0.12 plus 4 times 0.05. All right, and then you can put this all in your calculator, and we'll just round to 1 decimal place since there's no decimal places here, right, in the values of x. So I'm going to round it to 2. Oh, no, 1.9. Okay, easy enough? Now let's get the variance. So variance, sigma squared, that's going to be the sum of x squared times p of x minus mu squared. So now what you're going to do is take each of the values that the variable takes on, and we're going to square them this time. So I'm going to have 1 squared, don't touch the probability, that stays 0.32, plus 2 squared, don't touch that probability, 0.51. Keep it going, plus 3 squared times 0.12 plus 4 squared times 0.05. You see how it's working? And then last thing, you subtract mu squared. Oh, it's 1.9 squared. Okay? What I think to myself to help remember the formula is that every single term has something squared. And only one something squared. So don't square the probabilities. That'll mess you up. The x's get squared, and then minus mu squared. Okay, this is going to come out to 0.6. And then lastly, to get sigma, you just take the square root of sigma squared. And I'm not rounding until the last step. So what I mean is my calculator is saying more than just 0.6. I'm going to take the square root and then round. So for sigma, you should get 0.8. Okay. Good. How are we doing with the computations? Okay. Now the question for part B says, if you were taking a survey on the programs that were watched on television, how many program diaries would you send to each household in the survey? So basically, you should send 1 program diary for every television that's in that house. And the smartest thing to do is to just send everybody what the average number of TVs is per house, what the mean is. So what's the expectation? What was the mean number of televisions in a home? Well, we computed mu and it was 1.9. So it looks like if we send 2 program diaries to everybody, that should do the job, right? So 2 because mu was 1.9. I mean, there's, a nice chunk of people who have more TVs than that, so 2 wouldn't cut it. So I don't know how tight of a budget you have. I mean, I really need more information, but based on what they gave me, I'd say 2. Okay, next part, based on the probability distribution above, what is the probability that a randomly selected household has more than 2 televisions? Is it likely that a household has more than 2 televisions? So probability of more than 2 would be probability of 3 or probability of 4. So that would be the probability that x is equal to 3 plus the probability that x is equal to 4. And up here I have those probabilities, so I can just add them up. 0.12 plus 0.05, and this gives us 0.17. Okay, so 17% chance that a randomly selected household has more than 2 TVs. Is it likely that they have more than 2 TVs? Likely means more than a 50% chance, or more than 0.5. And I would say no, then this is not likely, because 0.17 is less than 0.5. All right, so that's it. Good. Now, another scenario where the mean or expected value of some random variable is used has to deal with gambling as well as insurance policies. So we're going to look at some examples. A lot of the time students ask me, when am I ever going to need math in real life? Well, there's plenty of day-to-day situations where you probably don't realize there's a lot of math going on behind the scenes. For example, casinos plan things out so that they always win. First one, if a player rolls 2 dice and gets a sum of 2 or 12, she wins $20. If a player rolls a sum of 7, she wins $5. The cost to play the game is $3. Find the expectation of the game. So find mu, or find the long run average for this game. All right, so let's think of what the values are that X can take on. X being your earnings, right, from playing the game. You have 2 different ways that you could win. You could win big. You could win $20, or you could win $5. Or saddest outcome of all is you just lose. And in that case, you would lose whatever you paid to play the game, right? So it looks like there's 3 different outcomes, or 3 values that X could take on. So we'll list them, and then we're going to have to compute the probabilities because they didn't give that to us either. So say you win $20, right? Your net winning really isn't $20 because you had to pay $3 to play the game. So what's your actual profit if you won big, $20? It's 17, right? Because you have to subtract the $3 that you paid to play. The other amount that you could win is $5. But again, remember you paid $3 to play. So then that win would be a net of how much? Just 2. Good. Or saddest outcome of all, you lose, you don't win, in which case you're in the hole $3, so -3. All right, now we have to compute each of the probabilities. So this game comprises of something really simple. You're just rolling 2 dice. And do you remember a few sections ago, we looked at what the sample space was for rolling 2 dice, how many outcomes there were total, and the total number of outcomes is 36, right? You have 6 outcomes on one die, 6 on the other. So 6 times 6 gives you 36 outcomes total when you roll 2 dice. If you're going to win $20, that happens because you rolled a 2 or a 12. So how many ways can you roll a 2? Only if you roll a 1 and a 1, right? And then how would you roll a 12? Only if you roll a 6 and a 6. So how many different ways could you win $20? It could only happen 2 different ways, right? And there's 36 different ways that you could roll 2 dice, 36 different outcomes. So the probability that you're going to win big, that big prize, is 2 out of 36. All right, I'm not going to reduce it. You'll see why in just a second, okay? All right, now the other way you could win, not as big, is if you roll a sum of 7, and they probably aren't paying you much because it's easier to roll a 7, right? So let's think, how could you roll a 7? 1 and a 6, 6 and a 1, 2 and a 5, 5 and a 2. Anything else? Yeah, 3 and a 4. Ooh, 3 and 4, or 4 and 3. Okay, so how many different ways could you win here? There's 6 different outcomes, right? So 6 divided by 36. All right. Well, all of the other outcomes would result in you losing. And I know the sum of all of the probabilities has to be 1. So notice if I have 2 out of 36 and 6 out of 36, Altogether, that's 8 out of 36. So what's left? So 36 out of 36 minus 8 out of 36 means I have 28 ways I could lose. So that's the probability of just losing, rolling anything other than a 2, a 12, or a 7. Okay? Good. The hardest part's over. We already filled in our probability distribution. Now we just have to figure out the expectation of the game. So expectation of the game is the same as mu, right? The long run average. You could write mu, or sometimes you might see it written E of X, expectation of X. And that's the sum of X times P of X. So this is going to give us, take each of the X values, 17 times their probabilities, 2 over 36, plus 2 times 6 over 36, plus, or you can just do subtract 3 times 28 over 36. Right? And then punch this all in your calculator. Let's round to 2 decimal places because this represents money. So up to the penny is all we need. And what do you guys get? Do you have negative 1.06? Good. Perfect. Okay. So what does that mean? That means in the long run, if you keep playing the game, right, your average is that every single time you play, you're going to lose $1.06. What does that mean for you as a gambler? If you're ever in the plus, walk away, okay? Because in the long run, you're set to lose. Every casino will set it up this way. They reel you in, you think you can win bigger, but you guys, the long run average is negative for you, positive for them. So get out while you can, okay? Let's look at another example, maybe a little depressing, maybe not, about life insurance. So a 35-year-old woman purchases a $100,000 term life insurance policy for an annual payment of $360. Based on a period life table for the U.S. government, the probability that she will survive the year is 0.999057. Find the expected value of the policy for the insurance company. So we are setting up X, the values that X could be based on the insurance company's perspective, okay? So what could happen to this insurance company? Really only one of 2 things, okay? Either she dies and they have to pay out the $100,000 policy. However, she did pay them $360, so they're not paying out a full $100,000. They're paying out $100,000 minus $360. So the insurance company would be out $99,640. All right, that's one option. If this woman dies, she dies. The other option is she survives the year, she lives, and they get $360 from her, and that's it. All right, so those are the 2 values that X can take on from the insurance company's point of view. Now, what's the probability of each of these things happening? Well, it's been calculated for this woman that the probability that she's going to survive, that she's going to live through the year is 0.999057. Where did that come from? There's all sorts of math that goes on behind the scenes, okay, taking into account her age, average, health, this and that. So that's not just a random figure that the insurance companies pull out of nowhere. The probability that she's going to die, how would we compute that? Well, we know that the probability that she lives or dies needs to sum up to 1 or 100%. So we'll just do 1 minus 0.999057. And this will give us 0.000943. Okay? Very good. So now we can figure out the expected value of this policy, E of X, from the insurance company's point of view. I'm going to take each of the values, negative 99640 and then multiply by the probability 0.000943 plus 360 times 0.999057, right? And then if you put this all in your calculator, you should end up with positive $265.70. So long run average, the insurance company will profit $265.70. So a lot of the time, insurance companies will hire actuaries. Those are people who've studied mathematics and probabilities to set what these annual payments should be based on how big of a policy is purchased and the person's, life expectancy and whatnot. So there's so much math that goes on behind setting these premiums. Okay, enough with morbidity. Let's go back to gambling. Maybe it's a little more fun. An American roulette wheel contains 38 numbers. 18 are red, 18 are black, and 2 are green. When the roulette wheel is spun, the ball is equally likely to land on any of the 38 numbers. Suppose that you bet $1 on red. If the ball lands on red, then you win $1. Otherwise, you lose your dollar. Let X be the amount you win on your $1 bet. Then X is a random variable whose probability distribution is as follows. So X can take on the values 1 or -1. And they gave us the respective probabilities. We could have computed it, but I guess they're feeling sorry for us. Okay, so verify that the probability distribution is correct. Well, what we need to do is just make sure that these indeed sum to 1, right? So let's just double check. 0.474 plus 0.526. Yep, that gives me 1.000. So we're good. Find the expected value of the random variable X. All right, so they've already given us the values in the table here. We're just going to go ahead, use the formula, same as the mean formula. Take 1 times 0.474 plus -1 times 0.526. And this is going to be -0.052. So on average, how much will you lose per play? Well, that's what the expectation tells us. It tells us on average, you're losing 5.2 cents. So 0.052, or you could just say, or you lose 5.2 cents. I don't know if we write it like that anymore. On average, every time you play the game, that's how much you're going to lose. Approximately how much would you expect to lose if you bet $1 on red 100 times? Well, if you're losing 0.052 every single time, then if you play 100 times, you're just going to multiply that by 100. So you would be losing $5.20. If you played 1,000 times, then same thing, you would lose 0.052 cents. $0.052 really, right? I'm keeping it in dollars, times 1,000. So you would lose $52 if you played 1,000 times on average. That's how much you should expect to lose. Is roulette a profitable game to play? Explain. Well, profitable for who? Not for me. So I would say, no, it's not profitable. For the casino it is, right? On average, you're losing. So the only way to make it profitable is walk away when you're winning. Okay, so please have some self-control. If you go to Vegas, remember this lesson and walk away. All right, that concludes the lecture for 5.2. Later on, coming up next, 5.3 is the binomial distribution and 5.4 the Poisson distribution. Stay tuned.